The marginal rate of substitution is closely related to the shape of the indifference curves. We're going to look at four classes of utility functions that show up often enough that they're worth giving special attention to. The first is perfect substitutes. The second is perfect complements. Then we've got these class of imperfect substitutes type of preferences, which include Cobb-Douglas as an example. And finally, quasilinear preferences. So let's look at each of these four in turn, and as the course progresses, these preferences will come up over and over again. So let's start with perfect substitutes. Let's say you have good 1 as being Pepsi and good 2 is Coke. Moreover, let's say that you can't actually taste a difference between the two. Then what's your marginal rate of substitution between these two? Well, your marginal rate of substitution is going to be -1. You're always going to be willing to trade 1 can of Coke for 1 can of Pepsi and vice versa. And if that's the case, we'll say that Pepsi and Coke are perfect substitutes. So perfect substitutes function, utility function, is u of q1, q2 is q1 plus q2. So your utility from q1 cans of Pepsi and q2 cans of Coke is just the total number of cans of cola that you get to drink. So your marginal utility from Pepsi is 1, your marginal utility from Coke is 1, so your marginal rate of substitution is -1 divided by 1, which is -1. So what do indifference curves look like for somebody who has perfect substitutes utility function? Well, they're just going to be these straight lines of slope -1. Right? So the utility from any given bundle comprised of 5 cans of Coke is just 5, or 5 cans of Pepsi, or any combination thereof is just going to be 5. So this is 5 cans of Pepsi and no cans of Coke, 5 cans of Coke, no cans of Pepsi, or any combination is on that line as long as you have 5 cans. And they all give you the same utility. And what's the slope of that line? It's -1. And that's indeed your marginal rate of substitution. And that's true for any number of cans that you get to drink. Now, we'd still use the term perfect substitutes even if you didn't have the slope -1. So let's suppose you had on the horizontal axis, so for good 1 you had cans of Coke, and the vertical axis you had 6 packs of Coke. So what utility function would represent your preferences over bundles Q1, Q2? If what you care about is the total number of cans that you consume, then this would be a utility function that represents that. So if you have Q1 individual cans and Q2 6 packs, how many total cans do you have? Well, you have the number of 6 packs times 6 plus the number of individual cans. So what's your marginal rate of substitution? Your marginal rate of substitution is calculated by getting your marginal utility. So your marginal utility from good 1 is 1. Marginal utility from good 2 is 6. So your marginal rate of substitution is -1/6. That means that your indifference curves are just going to be straight lines that have the slope -1/6. I'll let you figure out how those would look. So you just draw these axes, put 6 packs here, cans here, pick a bundle. So let's say this is comprised of, let's say, 3 6-packs and 2 cans. Draw an indifference curve through that point, through all the other bundles where you're indifferent between them. You'll find that it's going to be a straight line of slope -1/6. So more generally, perfect substitutes are those utility functions that take the form utility from Q1, Q2 is some number I times Q1 plus some number j times Q2. So your marginal utility from good 1 would be I, your marginal utility from good 2 would be j, and so your marginal rate of substitution would be minus u1 over u2, which is just minus I over j. So you would always need I over j units of good 2 as a perfect substitute for 1 unit of good 1. The next class of utility functions that we'd look at, or the next class of preferences we'd look at, are perfect complements. So one of these goods is going to be useful to you only if you have it in the same amount as the other good. So think of left shoes and right shoes if you have 2 feet. Say you had 10 right shoes and 6 left shoes. Then I offer you 1 more right shoe. So you have 4 extra right shoes already. Does the additional right shoe make you any better off? No, it doesn't. On the other hand, let's say you had 6 right shoes and 10 left shoes, and I offer you an additional left shoe. Again, you have more left shoes than right shoes this time, and I offer you 1 more of the thing that you have more of. Again, it doesn't help you at all. You're not going to be better off. So what you care about is the minimum of the number of left and right shoes that you have, because that's the number of pairs that you could put together. So if you have 10 right shoes and 6 left shoes, then you have 6 pairs. You have 6 right shoes and 10 left shoes, you still have 6 pairs. So your utility is the number of pairs of shoes that you have. So left shoes and right shoes are perfect complements. So you only really want to consume these bundles where you have Q1 equals Q2. Having extra units of either of the goods doesn't really help you. So how do your indifference curves look? Well, they look like these L-shaped things. Why is that? Take some bundle here. So you've got here more of good 1 than you have of good 2. You have, let's say, 3 and change of good 1. You have 2 of good 2. So if I give you more of good 1, you're not going to be any better off, as long as I don't give you any more good 2. So you're going to be on the same indifference curve. And if I reduce the number of units of good 1 that you have, you're still not going to be any worse off until I get to the point where you have equal numbers of good 1 and good 2. Now from that point, if I start to give you more of good 2 without giving you any more of good 1, again, you're not better off. You stay on your indifference curve. So that's why you end up with these L-shaped indifference curves. Again, more generally, we could formulate perfect complements not to be in these 1-to-1 ratios. So let's consider a very picky version of the Cookie Monster who says, I have to have 1 glass of milk and 3 cookies in exactly that ratio all the time. So he always wants to consume these bundles that comprise of 3 cookies for every glass of milk. So he wants to consume a bundle where the quantity of cookies equals 3 times the quantity of milk. In this case, his preferences would be described by a utility function of the form minimum of 3 times the quantity of milk or the quantity of cookies. If you had more left shoes than right shoes, how many right shoes would I need you to give to compensate you for taking away a left shoe? And the answer is none. Because the extra left shoes aren't worth anything to you. They don't actually help you at all. So that extra left shoe, the last extra left shoe, is completely useless to you. So your margin rate of substitution is actually 0. On the other hand, if you had fewer left shoes than right shoes, how many right shoes would I need to give you to compensate you for giving up a left shoe? The answer is infinitely many, because I couldn't give you enough. Because right shoes are worthless to you. You have fewer left shoes than you have right shoes. So giving you all the right shoes in the world wouldn't make up for taking away a left shoe, because it wouldn't give you an extra pair. So your margin rate of substitution here is negative infinity, and your margin rate of substitution here is 0. At the corners, however, you don't have a well-defined margin rate of substitution, because there's a kink in your utility function. And this comes from the fact that the minimum function isn't differentiable there. We don't worry too much about that. Okay, now what about imperfect substitutes? We've seen perfect substitutes, we've seen perfect complements. What about in between? So imperfect substitutes lie in between those two. So a utility function that gives you an indifference curve kind of like this, somewhere between the perfect complements and the perfect substitutes, indifference curves would be an imperfect substitutes utility function. Now there's lots of examples of these types of utility functions. So Cobb-Douglas is the common one. So for some a between 0 and 1, your utility function is q1 to the a, q2 to the 1 minus a. There's other ones too. We won't see this one as much in this course, constant elasticity of substitution, but there's plenty of these types of things. Typically, the reason you get this is because you have a diminishing marginal rate of substitution. This thing is getting flatter and flatter as you go to the right. However, you see that the indifference curves never touch the axes. And that's always going to be true of, especially of these Cobb-Douglas utility functions. And that makes some of the things we're going to do later in the course very, very easy. For example, when we do constrained optimization and you want to use a first order condition, you're always going to get an interior solution. Now there are preferences where that's not going to be true, like quasi-linear preferences. So quasi-linear preference is one where the utility function is such that your utility from q1, q2 is some function u of q1 plus q2. Why quasi-linear? Well, it's linear in one of the two terms. And we're going to assume that typically that u is an increasing and concave function. So your utility, marginal utility from good 1 is just, if we take the derivative of this with respect to good 1, well, that's just a constant. Utility, so you take the derivative of this, it's just a derivative of this little u with respect to good 1. And what's the marginal utility with respect to good 2? Well, you take the derivative of this with respect to good 2, you just get 1. So the marginal rate of substitution is just minus u1 over u2, so it's just negative of the derivative of little u. What's notable here is that the marginal rate of substitution depends only on q1. It doesn't depend on q2 at all. So this is going to give your indifference curves a very particular shape. So let's take an example. Let's say we have little u is 4 times square root of q1. So your utility function is 4 times square root of q1 plus q2. So your marginal rate of substitution is minus 2 divided by square root of q1. Right? It's just going to be the negative of the derivative of this thing. Now these indifference curves are always going to cut the axes. However, the slope of the indifference curve only depends on q1. So take any q1, if you draw a vertical line, every point here, the indifference curve has the same slope. Again, same thing here. Slope here, and slope here. All these points have the same marginal rate of substitution. And that's something particular about quasi-linear preferences. Now the fact that these do cross the axes is going to be important later. And we'll get to that. Just remember that. Okay, so far we've looked at preferences that had these nice shapes. They look like that. Those are what we call convex preferences. What about non-convex preferences? Right, so these nicely shaped preferences are convex preferences, and they denote that people have a preference for mixtures of two goods, like Cookie Monster, who likes to have a combination of milk and cookies. And it means that there's diminishing marginal rate of substitution. However, it's not necessarily always going to be the right assumption. So think of two goods, beer and liquor, Q1 and Q2. Convexity implies that if you compare three bundles, A, B, and C. So let's suppose you were indifferent between A and B. Then if you take some C that's on the line between A and B, convexity says that you have to think that C is a better bundle than both A and B, which might not be true. What if you don't like mixing the two? Well, in that case, your preferences might look more like this. In this case, A and B are on a higher indifference curve than C. Now, these indifference curves are going to be bowed away from the origin. And we call them non-convex preferences. Now, are these preferences monotonic? I think they are. They still do satisfy they're not inconsistent with the idea of more is better. But do they have diminishing marginal rates of substitution? And that's not really true.